modern data centers are hitting fundamental thermal limits. This presentation introduces a patented architecture that moves cooling from the room and rack level down to the substrate itself, using supercritical CO₂ as a high-efficiency heat transport medium, integrated with LifeStack photonics and AI-driven collective management. Today's data center cooling strategies were never designed for sustained high-density compute. Air cooling is reaching physical limits, water usage is increasingly constrained, and retrofits are costly, fragile, and slow. As AI and high-performance computing workloads intensify, these challenges are becoming critical barriers to infrastructure scaling. Incremental fixes, more airflow, more liquid loops, more containment, add complexity without addressing the root problem. Heat is still being managed after it spreads, instead of being extracted at its source. This reactive approach leads to thermal gradients, hot spots, and unpredictable failure modes. The invention proposes a fundamental shift. Cooling should not be something wrapped around compute. It should be embedded directly into the physical backplane where heat is generated. This transforms cooling from an external system into an integral part of the infrastructure itself. At the core of the system is an integrated thermal backplane. This backplane serves both as a structural component and as the primary heat transport interface for high-density compute hardware. Heat flows directly from processors into embedded microchannels, eliminating intermediate thermal interfaces and resistance. Supercritical CO₂ is used as the working fluid because of its exceptional thermodynamic properties. Above its critical point, CO₂ behaves as a dense fluid with gas-like transport and liquid-like heat capacity, without phase change instability. This enables efficient heat transfer at moderate temperatures and pressures. Unlike water or refrigerants that rely on phase change, supercritical CO₂ enables stable, single-phase heat transport even under extreme thermal flux, eliminating evaporation losses and water dependency. The fluid remains in a consistent state, allowing for precise thermal management and predictable system behavior across varying computational loads. Heat flows directly from compute modules into embedded microchannels within the backplane, where supercritical CO₂ transports it efficiently to external heat rejection systems. Simultaneously, LifeStack photonics links all backplanes into a unified management fabric, while AI continuously monitors sensor data and orchestrates thermal optimization across the entire data center, transforming passive cooling into intelligent, adaptive infrastructure. Beyond cooling, each thermal backplane integrates into LifeStack, a photonics-based management fabric that links every backplane in the data center into a unified, intelligent system. This optical interconnect provides high bandwidth, low latency communication between backplanes, enabling real-time coordination and collective thermal optimization across the entire facility. Sensors are embedded at every critical point throughout the backplane, monitoring temperature, pressure, flow rate, and thermal gradients. Artificial intelligence continuously analyzes this sensor data, building predictive thermal models, detecting anomalies before they become failures, and autonomously balancing thermal loads across compute resources to maximize efficiency and reliability. The result is a collective intelligence architecture where cooling is no longer passive infrastructure. It becomes an active, self-managing system. AI orchestrates thermal capacity across the facility, predicting optimal workload placement, preemptively redistributing heat loads, and enabling self-healing responses to component degradation. The thermal backplane is simultaneously cooling infrastructure, sensor network, and intelligent control plane. The BEC Panel, backplane electronics, and cooling is a unified infrastructure substrate where thermal management, power distribution, high-speed data interconnects, and intelligent control converge into a single physical platform. This integration eliminates the traditional separation between cooling, power, and networking infrastructure, creating a holistic system where every function is monitored, managed, and optimized by AI through the LifeStack fabric. When maintenance is required, the AI can selectively isolate individual racks or drawers, shutting down power and communications to the target hardware while keeping adjacent infrastructure fully operational. This intelligent isolation enables hot swap maintenance, component replacement, and service operations without disrupting the broader facility. The system monitors component health and can proactively schedule maintenance before failures occur, maximizing uptime and operational efficiency. By integrating cooling at the backplane, thermal gradients are flattened, hot spots are eliminated, and scaling becomes predictable rather than chaotic. Each compute node has direct access to cooling capacity, eliminating thermal competition and ensuring consistent performance across the entire system. The system includes multiple layers of thermal resilience. If the primary supercritical CO₂ system experiences degradation, a passive ground-coupled thermal loop provides secondary cooling. In emergency scenarios, thermoelectric devices recover waste heat to power fan-based air exchange, requiring no grid power or batteries. This ensures graceful degradation rather than catastrophic failure. Compared to conventional approaches, this architecture reduces complexity, eliminates water dependence, and moves thermal management into the physical structure itself. The result is a system that is simpler to operate, more resilient to failure, and fundamentally more scalable than traditional cooling infrastructure. CO₂ is non-flammable, non-toxic, and already used in industrial thermal systems worldwide. The closed-loop design improves reliability and reduces long-term maintenance risks. Unlike water-based systems, there is no mineral buildup, no biological growth, and no corrosion from dissolved oxygen. The system may be deployed in surface, partially subterranean, or fully subterranean environments, including excavated, bored, or geologically stable structures. Underground deployment offers stable ambient temperatures, massive thermal inertia, natural electromagnetic and physical shielding, and near-zero visual or acoustic footprint, making it ideal for sovereign, defense, or long-term resilient infrastructure. Compared to space-based data centers, underground facilities avoid launch costs, orbital debris risk, communication latency, and constant repositioning requirements, while achieving superior thermal efficiency. The Earth itself provides passive cooling capacity, radiation shielding, and physical security without ongoing operational complexity. The architecture scales across deployment models, from hyperscale facilities to edge compute, and is particularly well-suited to subterranean data centers where thermal stability and water independence are critical. The modular nature of the backplane allows for incremental capacity expansion without redesigning the entire cooling infrastructure. By re-architecting cooling at the substrate level, this system unlocks higher compute density, lower operating costs, and long-term sustainability without relying on scarce water resources. Facilities can operate at higher utilization rates with greater reliability, reducing both capital and operational expenditure over the infrastructure lifecycle. The integrated supercritical CO₂ thermal backplane with LifeStack represents a convergence of thermodynamic efficiency, structural integration, operational resilience, environmental responsibility, strategic flexibility, and artificial intelligence. By combining advanced cooling with photonics-based networking and AI-driven management, it creates a self-aware, self-optimizing thermal infrastructure that positions data centers for the next generation of high-density, intelligent computing demands. The integrated supercritical CO₂ thermal backplane with LifeStack transforms cooling from a supporting system into intelligent, networked infrastructure, where thermal management, sensing, and AI-driven optimization converge. This is not an incremental improvement. This is a fundamental reimagining of how we build adaptive, resilient thermal infrastructure for the computational age.